So solution stoichiometry. So molarity relates moles of solute to liters of solution. So it can be used to convert between amounts of reactants or products in a chemical reaction. So the general conceptual plan here is the volume of A to amount of A in moles to amount of B in moles to volume of B. So this is a variation of grams to moles to moles to grams. Grams to moles to grams. If instead of putting a solid into my beaker to react it, I'm going to measure out a volume of a solution, then instead of having grams here, I might have liters. I know the concentration, and so I can convert from liters to moles using the molarity. And then moles to moles using the coefficients from the chemical equation. And then I might want to find the mass of something at the end, or I might want to find the volume. But it's a variation on grams to moles to moles to grams, where we're using molarity instead of molar mass as the conversion factor. So let's do an example. And solution stoichiometry is very, very common. What volume in milliliters of a 0.150 molar nitric acid solution will completely react with 35.7 milliliters of a 0.108 molar sodium carbonate solution according to the following balanced chemical equation? So there's our balanced chemical equation. This is stoichiometry. We've got amounts of stuff, and we've got a chemical equation. There's a chemical reaction going on. So I'm going to pull those numbers out and write them under the balanced chemical equation. So this 0.150 molar nitric acid. So I'm going to find that in the equation, 0.150. And I'm not going to write capital M. I'm going to write moles per liter. A question in the back.
I have a side question. As far as the balanced equations and stuff, will there ever be an unbalanced equation that you don't tell us?
That's a good question. Will there ever be an unbalanced equation that you have to balance? Yes, there certainly could be.
No, I mean that you don't tell us about
Like I don't point it out?
Yeah, like say you just say that just said solution according to the following chemical equation. Like should we
It's always a good idea to double check that it's balanced. It's usually pretty safe to assume it's balanced if you see some coefficients. If there aren't any coefficients, it could be a trap. But like on an exam, I might do that to you, but it will usually say, according to the following unbalanced chemical equation, which is your big clue that, hey, I need to balance this first. But yeah, that is something to watch out for. So I've got the concentration in there, and then the next number I've got is 35.7 milliliters of this guy. So I'm going to write that under its formula, 35.7 milliliters. And then it also tells me 0.108 molar for that substance, moles per liter. And then I have to ask myself, well, what's the question? What volume in milliliters of this guy? So question mark milliliters. So stoichiometry is grams to moles to moles to grams. But I'm not starting with grams, I'm starting with a volume. So I'm starting with milliliters over here, and then it's asking me to find milliliters at the end. This is going to be a bit like those problems we did where it was kilograms to kilograms, but the things in the middle here we were using weren't kilo, and so one way to do it is convert milliliters to liters, and then to moles and to liters and back to milliliters. Or we can use the same strategy of just setting aside the milli and bringing it back at the end. Or we can use something called millimoles. But we'll not talk about those just yet. So I'm going to start with the volume of the sodium carbonate. So I've got 35.7, and I'm going to put that milli in red because I'm just going to let it ride. Milliliters of sodium carbonate. And then I'm going to go from that volume to moles of sodium carbonate. Record. To moles of sodium carbonate. And then what's next? Moles of the nitric acid. Moles of HNO3. And then here at the end, I'm just ignoring the milli part. This would be liters of HNO3. Because what I've got is I have moles per liter for the sodium carbonate. And that's going to cancel liters of sodium carbonate. It's not going to cancel the milli. I'm just going to leave it. And my mole ratio in here. And then over here, liters per mole. It's upside down molarity. And those will cancel. So then if I look at the units, the milli was not canceled. All these other things in the middle were canceled, and the liter wasn't canceled. And so at the end here, what I've got is milliliters. Yes? That's an excellent question. And it's super, super tempting. Why am I not using M1V1 equals M2V2? Am I diluting a solution? No. I'm doing a chemical reaction. So I have a volume and a molarity of one substance, and I'm looking at volume and molarity of a different substance. And so that is different than titration, where I've got one compound. Now, it's very tempting, and the really, really tricky thing is sometimes it works if you use the dilution equation. But what the dilution equation is missing is this mole ratio. It's 1 mole of this to 2 moles of that, and that will be missing in the dilution equation. Well, 1-to-1 is when if you have a 1-to-1 mole ratio, that's when it would work, but I still don't recommend doing that. Because this is not, once we get the hang of this is just like the grams to moles to grams, and it's really not any more difficult than using M1V1, and it's going to get you the right answer. So I think that's better. So dilution is when you have one compound. If you have 2 compounds, if they give you a chemical equation, don't do it. It's a reaction. You can't use it. So, any questions about the units? So, this is the relation between moles and liters of sodium carbonate. That's the molarity here. 0.108 moles for every liter. Well, I didn't leave enough room, so I'll write it sideways. 0.108 moles per 1 liter of sodium carbonate solution. The middle is my mole ratio from the balanced chemical equation. There's a 2 in front of HNO3. 2 moles of HNO3 for every 1 mole of sodium carbonate. And then at the end here, I've got moles and liters again of nitric acid, and I have this concentration, 0.150 moles per liter. So the moles is in the bottom, moles is where the number goes. I'm taking this and I'm inverting it, upside downing it. 0.150 moles, that goes in the bottom. Now, what's faster about this than grams to moles to grams? Did I need to calculate any molar masses? No. The concentrations are given to me. I just have to put them in. So chemists use solutions a lot. It makes the calculations go much, much faster because you don't have to calculate molar masses all the time. So now I just punch these numbers in my calculator. 35.7 times 0.108 times 2 divided by 0.15. I should have three significant figures. 51.408, 51.4 milliliters. Any questions? Chemistry is a very cumulative subject. The things we started talking about the first day, we just keep building and building and building, right? It's just going to keep building. And so if you're a bit lost right now, the sooner we find ourselves, the easier the rest of it will be. 51.4 milliliters. Conceptual connection. So this is probably not going to require a calculator. Consider this reaction. This is a generic reaction using letters instead of actual compounds. So 2A plus B makes C. And it's asking, what's the limiting reactant if you mix equal volumes of a 1 molar solution of A and a 1 molar solution of B? Well, equal volumes. So I've got 1 mole per liter of A, and I have 1 mole per liter of B. Those are the concentrations I was given. And it says I'm mixing equal volumes. So no matter what volume I take, if I take the same volume of each of them, the moles are going to be equal. So we can think of it that way, or we can just like pick a number and say, well, I'm going to say I have 1 liter of each. Is that equal volumes? Yeah, that's equal volumes. How many moles in 1 liter? 1? Yeah. So if I choose 1 liter, then I have 1 mole of A and 1 mole of B. Oops. It takes 2 moles of A for every 1 mole of B to make 1 mole of C. What am I going to run out of first? A, right? I'm going to run out of A. Because when I've used up 1 mole of A, I've only used up half a mole of B. In order to use all of this up, I would need 2 moles, and I don't have that. So this is the limiting reactant because that's the one that we're going to run out of. I can. How far back should I go? YA. Okay, so I'm just going to back up to where the point where we had 1 mole of A and 1 mole of B. And then we're trying to figure out, well, which one is going to run out? Which one's going to limit the amount? I look at this equation, I need 2 moles of A to react with 1 mole of B. Here I have 1 mole of B. I only have 1 mole of A. In order for this to completely react, I need 2 moles of A. See? And so that means I can use all this up, but then there's going to be some of this left over. This is the limiting reactant. And this is a conceptual problem because we're just looking at A's and B's. We're not going to get confused with molar masses or anything like that. And we're not doing any crazy numbers. We're just using nice whole numbers so that we can really see what we're doing. Is everybody okay with this? Do you see how it worked? They're saying equal volumes. The concentrations are equal. So no matter what volume I pick, if I have equal amounts, I'm going to have equal amounts of moles. If I have equal numbers of moles, I'm going to have something left over because I need twice as much A to react with B. If I have equal amounts, I'm going to run out of A first.